If you want to read Marie Curie's original research today, you must first sign a liability waiver and put on a lead-lined radiation suit. A century after her death, her notebooks, her furniture, and even her cookbooks are still dangerous to touch. Atoms within them are still decaying, still releasing a mysterious invisible fire. Most people know her as the woman who discovered radium. But what she actually found was much more unsettling. She discovered that the universe is not solid. Atoms are not eternal, and matter itself can leak energy until it vanishes. Tonight, we step into a freezing shed in Paris to find the woman who looked into the heart of the atom and found a light that never goes out, even when it's lethal. Welcome back to Sleep Entangled, where the greatest minds in science and the mysteries they uncovered merge into edutainment journeys. As you settle in and breathe slowly, let curiosity guide you. In this video, we follow the glowing trail of Marie Curie. Chapter 1. The Beauty of the Deadly Glow. In the early 1900s, visitors to Marie Curie's laboratory in Paris reported something that felt more like magic than physics. If you entered after dark, the room shivered with an eerie blue-green light. Vials on the shelves emitted a ghostly luminescence, and Marie herself, her clothing, her hands, even her hair, seemed to have absorbed the stars. She called it radioactivity. She did not know then that every breath she took in that laboratory was filling her lungs with radioactive dust. She didn't realize that the burns on her hands, wounds she thought were mere chemical irritations, were actually radiation damage penetrating her very cells. To Marie, the glow was simply beautiful. Working in a converted shed with a leaking roof, Marie Curie was the first human to systematically study the quantum lottery. She proved that atoms, the supposedly uncuttable building blocks of reality, can transform, decay, and spontaneously change into something else entirely. She gave her life to understand this mysterious fire. In doing so, she opened a door into the quantum world, a place where matter is not stable, and the only constant is change. Marie Curie discovered radioactivity, isolated radium and polonium, won 2 Nobel Prizes in different sciences, an achievement unmatched before or since, and in doing so, she opened a door into the quantum world. Because radioactivity revealed something profound and unsettling. Atoms are not eternal. They are not the stable, indivisible building blocks the ancient Greeks imagined when they coined the word atomos, uncuttable. Atoms can transform, they can decay, they can emit particles and energy, changing into different elements entirely, and no one can predict exactly when any individual atom will do this. Radioactivity is quantum mechanics in its purest form. Fundamental randomness, probabilistic decay, the impossibility of knowing when a system will collapse from one state to another. And Marie Curie, working with her bare hands in a freezing shed, was the first human to study this phenomenon systematically, to isolate it, to measure it, to begin understanding it. Her story is remarkable not just for the science but for the obstacles she overcame. Born Maria Sklodowska in Warsaw, Poland in 1867, she grew up in a country that did not exist as an independent nation, partitioned between Russia, Prussia, and Austria. Polish culture was suppressed. Higher education for women was forbidden. The universities in Warsaw would not admit her. So at age 24, she moved to Paris. She enrolled at the Sorbonne, one of the few universities in Europe that accepted women, and lived in a tiny, unheated attic room, surviving on bread and tea, studying physics and mathematics with single-minded intensity. She finished first in her master's degree in physics. She met Pierre Curie, a physicist who would become her husband and collaborator, and together they began investigating a mystery that had puzzled scientists since 1896. That year, Henri Becquerel had discovered that uranium compounds emitted rays that could expose photographic plates even when wrapped in black paper. No light was involved. No chemical reaction seemed to explain it. The uranium simply radiated energy continuously, spontaneously, without any apparent external cause. Becquerel didn't understand it. No one did. But Marie Curie decided to investigate. She began systematically measuring the radiation from various uranium compounds using an electrometer Pierre had designed to detect the tiny electrical currents the rays produced in air. She was meticulous, precise, quantitative, and she made a crucial discovery. The intensity of radiation depended only on the amount of uranium present, not on what compounds it formed, not on temperature, not on light exposure, not on any external condition. The radiation came from the uranium atoms themselves. This was revolutionary. It meant that atoms had internal structure, internal energy, internal processes that were not affected by chemistry or environment. The atom was not a simple inert particle. It was complex, dynamic, capable of spontaneous transformation. This contradicted everything classical physics assumed about matter. Marie Curie coined the term radioactivity to describe this phenomenon, and then she made another discovery that would consume the next 4 years of her life. When she measured the radioactivity of pitchblende, a uranium ore, she found it was far more radioactive than pure uranium, much more, as if the ore contained something else, something even more intensely radioactive than uranium itself. She was right. Pitchblende contained not one but 2 previously unknown elements, both radioactive, both present in tiny quantities. She would have to process tons of pitchblende to isolate even grams of these mysterious substances, and she would have to do it in a converted shed with a leaking roof, in freezing winter and sweltering summer, stirring boiling vats of toxic ore with an iron rod nearly as tall as she was. She did it anyway. For 4 years, she and Pierre refined pitchblende in conditions that would be considered inhumane in modern laboratories. No ventilation, no protective equipment, constant exposure to radioactive dust and fumes. Her hands became scarred and burned. Her health began to fail. But in 1898, they announced the discovery of 2 new elements: polonium, named for her beloved Poland, and radium, which glowed with such intense luminescence that it became a worldwide sensation. Radium became famous almost instantly. It glowed in the dark. It seemed to produce energy from nothing, violating the law of conservation of energy. It could burn skin, kill bacteria, cure certain cancers. People were fascinated and terrified in equal measure. Radium watches, radium cosmetics, radium tonics. Entrepreneurs hawked radioactive products as miraculous cures, unaware they were selling poison. Marie Curie remained focused on the science. She painstakingly determined radium's atomic weight, its chemical properties, its spectrum. She showed that radioactivity was an atomic property, that it came from the spontaneous disintegration of atoms, that elements could transform into other elements through this process. She had discovered transmutation. Not the medieval alchemy of turning lead into gold, but the actual physical transformation of one element into another through radioactive decay. In 1903, she shared the Nobel Prize in Physics with Pierre Curie and Henri Becquerel. She was the first woman to win a Nobel Prize. 8 years later, after Pierre's tragic death in a street accident, she won a second Nobel Prize, this time in chemistry, for isolating pure radium and determining its properties. She remains the only person ever to win Nobel Prizes in 2 different sciences. The cost was written in her body. The radioactivity that made her famous was destroying her cells, damaging her bone marrow, accumulating in her tissues. She suffered from chronic illness, fatigue, cataracts, anemia. Her fingers were permanently scarred and radiation burned. And on July 4th, 1934, Marie Curie died of aplastic anemia, a disease almost certainly caused by prolonged radiation exposure. Her notebooks, her laboratory equipment, even her cookbooks are still radioactive more than a century later, stored in lead-lined boxes at the Bibliothèque Nationale in Paris. To consult them, researchers must sign a liability waiver and wear protective clothing. The pages still glow faintly if you turn out the lights, atoms still decaying, energy still radiating, the physical echo of her life's work preserved in dangerous luminescence. But to understand the woman, we must first understand the mystery she chased. What exactly is this invisible force that can photograph your bones, heal a tumour, and yet remain deadly for 1,000 years? Chapter 2. What is radioactivity? Atoms that refuse to stay still. To understand what Marie Curie discovered, we need to understand what atoms are and why most of them stay stable while some do not. For most of the 19th century, scientists believed atoms were the smallest possible units of matter, tiny, solid, indestructible spheres that combined in different arrangements to form all the substances in the universe. Iron atoms, oxygen atoms, carbon atoms, each element had its own type of atom, and those atoms were eternal and unchanging. But in the 1890s, that picture began to crack. J.J. Thomson discovered the electron in 1897, proving that atoms had internal parts. They were not indivisible after all. Then Becquerel discovered uranium's mysterious rays, and when Marie Curie began studying these rays systematically, she realized something profound. The radiation was coming from inside the atoms themselves, and it was changing them in the process. Radioactivity is the spontaneous emission of particles and energy from unstable atomic nuclei. Let me break that down. At the center of every atom is a nucleus, a tiny, incredibly dense core made of protons and neutrons. Protons are positively charged, neutrons have no charge, and they are packed together so tightly that the forces holding them are among the strongest in nature. In most atoms, this arrangement is stable. The protons and neutrons sit comfortably together, balanced by nuclear forces, and the atom can exist for billions of years without changing. Carbon-12, for instance, the most common form of carbon, is perfectly stable. If you have a carbon-12 atom today, it will still be carbon-12 a trillion years from now. But some atomic nuclei are not stable. They have too many protons, or too many neutrons, or the wrong ratio between the two, and the nuclear forces cannot hold them together indefinitely. These unstable nuclei are radioactive, and eventually, sometime, somehow, they will decay, releasing energy and particles to reach a more stable configuration. Marie Curie and her colleagues discovered 3 types of radiation emitted during this decay, and they named them using the first 3 letters of the Greek alphabet: alpha, beta, and gamma. Alpha radiation consists of helium nuclei, 2 protons and 2 neutrons bound together, ejected from the decaying atom at high speed. Alpha particles are relatively large and heavy for subatomic particles. They do not penetrate far. A sheet of paper stops them, your skin stops them. But if an alpha-emitting substance gets inside your body, if you breathe radioactive dust or ingest contaminated material, alpha particles can cause severe damage to nearby cells. Beta radiation consists of high-energy electrons or positrons. particles with much less mass than alpha particles but higher penetration. Beta particles can pass through paper and skin, but are stopped by a few millimeters of aluminum or plastic. Beta decay happens when a neutron in the nucleus transforms into a proton, emitting an electron in the process, or when a proton transforms into a neutron, emitting a positron. Gamma radiation is pure energy, high-frequency electromagnetic waves like ultra-intense X-rays. Gamma rays have no mass and no charge. They're just photons, but photons so energetic they can penetrate deeply into matter. It takes thick lead or concrete to stop gamma radiation. This is the type of radiation used in cancer treatment. Focused beams that can kill tumor cells but require careful shielding to protect surrounding tissue. When Marie Curie worked with radium, she was exposing herself to all three types simultaneously. The radium emitted alpha particles as it decayed into radon gas. The radon emitted more alpha particles and gamma rays. Decay products down the chain emitted beta particles. Her laboratory was filled with invisible radiation, constantly bombarding her body, damaging cells faster than they could repair themselves. She did not know this at the time. No one did. Radiation was mysterious, seemingly magical. Radium glowed. It produced heat continuously without burning any fuel. It seemed to violate the law of conservation of energy, until Einstein's famous equation E=mc² revealed that mass itself is concentrated energy, and radioactive decay converts a tiny amount of nuclear mass into the energy carried away by radiation. Here is what makes radioactivity deeply strange from a physics perspective. It is fundamentally random. You cannot predict when any individual atom will decay. You can have two identical radium atoms sitting side by side in identical conditions. One might decay in the next second. The other might last another 1,000 years. There is no hidden clock ticking down inside each atom, no internal mechanism that determines the exact moment of decay. The process is probabilistic, governed by quantum mechanics. What we can measure is the half-life, the time it takes for half of a sample of radioactive atoms to decay. Radium-226 has a half-life of about 1,600 years. If you start with 1 gram of radium-226, after 1,600 years you will have half a gram of radium and half a gram of decay products. After another 1,600 years, you will have a quarter gram of radium. The sample keeps halving at a predictable rate. But which individual atoms decay when remains purely random? This randomness disturbed classical physicists. Einstein himself famously objected to the probabilistic nature of quantum mechanics, saying, "God does not play dice with the universe." But radioactive decay proved that at the atomic level, the universe does work through probability, through chance, through processes that cannot be predicted with certainty no matter how much information you have. Marie Curie did not work out all the quantum mechanical details. That would come later with physicists like Niels Bohr, Werner Heisenberg and Erwin Schrödinger. But she established the experimental foundation. She proved that atoms transform spontaneously. She measured decay rates precisely. She showed that radioactivity was a nuclear phenomenon, fundamentally different from chemical reactions, governed by forces and processes occurring at scales far smaller than chemistry could reach. And in doing so, she opened the door to nuclear physics, to our understanding of how elements form in stars, how the Earth generates internal heat, how carbon dating works, how nuclear power and nuclear weapons became possible. Radioactivity is not just a curiosity. It is one of the fundamental processes shaping the universe. Consider this. Your own body contains radioactive atoms. Potassium-40 in your cells, carbon-14 in your tissues, trace amounts of uranium and thorium you have inhaled or ingested from soil and water. Right now, at this very moment, atoms inside you are decaying, releasing tiny bursts of energy, transforming into different elements. You are, in a very real sense, slightly radioactive, and you always have been. Let us move now into how Marie Curie isolated these radioactive elements, into the extraordinary physical labour and scientific precision required to extract grams of radium from tons of ore. Chapter 3. The Radium Factory, 4 years in a freezing shed. When Marie Curie measured the radioactivity of pitchblende ore in 1898, she calculated that it contained approximately 1 part radium per million parts ore, 1 part per million. To isolate enough radium to study its properties, to determine its atomic weight, to prove it was a distinct element, she would need to process tons of raw ore to extract grams of pure radium. This was not theoretical chemistry. This was industrial-scale, manual labour. The University of Paris did not have facilities for this kind of work. The Curies had no funding for a proper laboratory, so they were given permission to use an abandoned dissection shed on the university grounds, a leaking wooden structure with a dirt floor, broken windows and no ventilation. In winter, the temperature inside dropped below freezing. In summer, the heat was suffocating. It was by any standard completely inadequate for scientific research. Marie Curie worked there for 4 years. The process of extracting radium from pitchblende required multiple stages of chemical separation, each more tedious than the last. First, she and Pierre had to obtain the raw ore. They arranged to buy tons of pitchblende residue from a uranium mine in Bohemia, the leftover waste after uranium had been extracted. The mine owners were happy to sell it cheaply. They thought it was worthless. The ore arrived in sacks. Marie Curie, often working alone, would transfer the ore into huge cast iron pots, add chemicals, and boil the mixture for hours, stirring with an iron rod nearly as tall as she was. The fumes were toxic. The work was back-breaking. She would spend entire days standing over boiling vats, inhaling radioactive vapour, her arms aching from constant stirring. After boiling, she would filter the mixture, precipitate out certain compounds, dissolve others, evaporate solutions down to concentrated residues. Each step required precision, each step generated waste, and each step left her with a smaller quantity of material that was slightly more radioactive than what she started with. The goal was fractional crystallization, repeatedly dissolving and recrystallizing salts to concentrate the radioactive element. Radium chloride and barium chloride have very similar chemical properties, but radium chloride is slightly less soluble. By dissolving a mixture in water and allowing it to crystallize slowly, Marie could separate out the radium fraction bit by bit, cycle after cycle. This process had to be repeated hundreds of times. Dissolve, crystallize, separate, dissolve, crystallize, separate, over and over, for months, for years. It was monotonous, exhausting work that demanded absolute precision. A single mistake could ruin weeks of effort. Marie Curie kept meticulous notebooks documenting every step, every measurement, every observation. She recorded the weight of each fraction, the radioactivity of each sample, the conditions of each crystallization. Her data was so precise that other chemists could replicate her work exactly, which was crucial for establishing radium as a genuine new element, rather than a measurement error or contamination. By 1902, after processing over 8 tons of pitchblende residue, Marie Curie had isolated approximately 1/10 of a gram of pure radium chloride, 1/10 of a gram from 8 tons of ore. That is roughly the weight of 2 grains of rice, extracted from the equivalent of a large car's worth of raw material. But that tiny sample was enough. She measured its atomic weight, 226, much heavier than barium, and determined its position in the periodic table. She studied its spectrum, its chemical behavior, its rate of radioactive decay. She proved conclusively that radium was a distinct element, not a compound of known elements, not an artifact of measurement. The work destroyed her health. Her hands became scarred and permanently damaged from handling radioactive materials. She suffered from chronic fatigue, dizziness, persistent coughs. Her fingers were burned so badly that she lost the ability to feel texture in her fingertips. Medical examinations later showed severe radiation damage to her bone marrow and internal organs. Pierre Curie also suffered. He experienced severe pains in his legs and back, chronic fatigue, and difficulty sleeping. In one experiment, he deliberately exposed his arm to radium to study the burns it caused. The wound took months to heal and left a permanent scar. Both of them understood that radium was dangerous, but neither fully grasped how dangerous. Radiation damage is cumulative and invisible. By the time symptoms appear, significant harm has already occurred. Despite the physical toll, Marie Curie continued. After Pierre's death in 1906, killed in a street accident when he slipped on wet pavement and was run over by a horse-drawn wagon, she took over his teaching position at the Sorbonne, becoming the first female professor there. She continued her research. She established the Radium Institute in Paris, training a new generation of physicists and chemists, and in 1911 she won her second Nobel Prize for her work on radium isolation and characterization. The shed where she performed this grueling work no longer exists. It was demolished decades ago. But photographs remain, images of Marie Curie standing beside enormous vats, holding her stirring rod, surrounded by sacks of ore and rows of glass vessels. She is small, serious, her expression focused. There is no laboratory equipment visible beyond the most basic tools, no modern safety gear, no protective clothing. Just a scientist, alone in a freezing shed, processing tons of toxic ore by hand to isolate a substance the world had never seen before. That kind of determination, that willingness to endure years of brutal physical labor for the sake of understanding, defined Marie Curie's approach to science. She did not wait for better conditions. She did not demand proper facilities before beginning. She worked with what she had, and she succeeded through sheer persistence and precision. The radium she isolated glowed blue-green in the dark. Visitors to her laboratory reported that vials on shelves emitted light, that samples glowed like captured moonlight. Marie Curie found it beautiful. She would sometimes visit the shed at night just to look at the luminous samples, to see the physical manifestation of radioactivity glowing in the darkness. She did not know that every glowing vial was slowly killing her. That beauty was deadly. But even if she had known the full risk, it is difficult to imagine she would have stopped. The drive to understand radioactivity, to isolate these mysterious elements, to reveal the hidden properties of matter, that drive defined her life. Let us move now into what radium and radioactivity revealed about the nature of atoms, into the quantum mechanics underlying decay, into why some nuclei are stable, while others fall apart. Chapter 4: Alpha, Beta, Gamma, the three faces of decay. When Marie Curie and Ernest Rutherford first studied radioactive emissions in detail, they found that the radiation could be separated into three distinct types by passing it through magnetic and electric fields. Some particles curved one direction, others curved the opposite direction, and some passed straight through unaffected. They labelled these three types alpha, beta, and gamma, and each turned out to reveal different aspects of how atomic nuclei transform. Alpha decay is the simplest to understand mechanically. An alpha particle is a helium nucleus, 2 protons and 2 neutrons bound tightly together. When an unstable nucleus emits an alpha particle, it loses 4 units of mass and 2 units of positive charge. The atom literally changes identity, transforming into a different element 2 spaces down on the periodic table. Uranium-238, for instance, undergoes alpha decay to become thorium-234. The uranium nucleus ejects an alpha particle, and what remains is no longer uranium, it is thorium. This is transmutation in the truest sense, one element becoming another, not through chemical reaction but through nuclear transformation. The medieval alchemists dreamed of turning lead into gold. Radioactive decay accomplishes something similar, though the transformations follow fixed pathways determined by nuclear stability, not human desire. Alpha decay occurs in very heavy elements, uranium, thorium, radium, plutonium, where the nucleus has become so large that the electromagnetic repulsion between all those positively charged protons begins to overwhelm the strong nuclear force trying to hold everything together. The nucleus becomes unstable, and ejecting an alpha particle reduces its size, moving it toward a more stable configuration. The alpha particles themselves are relatively slow and heavy compared to other forms of radiation. They carry a lot of energy but do not penetrate far. A piece of paper stops them. The outer layer of dead skin on your hand stops them. This is why alpha emitters are relatively safe externally. You can hold a small sample of uranium without much danger from the alpha radiation, but if you inhale alpha-emitting dust, if it gets into your lungs or digestive system, the damage is severe. The alpha particles released inside your body deposit all their energy over a very short distance, hitting cells with concentrated bursts of ionizing radiation. This is what happened to Marie Curie. She breathed radioactive dust for years, and alpha particles destroyed cells in her lungs and bones where external alpha radiation would have been harmless. Beta decay is fundamentally different. It involves the transformation of a neutron into a proton, or vice versa. When a neutron decays into a proton, it emits an electron, a beta- particle. The atom gains a proton, which means it moves 1 space up on the periodic table, becoming a different element. Carbon-14, for example, undergoes beta decay to become nitrogen-14. The carbon atom literally transforms into nitrogen by changing one of its neutrons into a proton. There is also beta plus decay, where a proton transforms into a neutron, emitting a positron, the antimatter counterpart of an electron. This happens in certain unstable isotopes that have too many protons relative to neutrons. The positron is ejected, the atom loses a proton, and it becomes a different element 1 space down on the periodic table. Beta particles are much smaller and faster than alpha particles. They penetrate farther, through paper, through skin, but not through a few millimeters of aluminum or plastic. Beta emitters require more shielding than alpha emitters, but less than gamma emitters. The physics of beta decay reveals something profound about the nature of subatomic particles. Neutrons and protons are not fundamental, unchanging objects. They can transform into each other through the weak nuclear force, one of the 4 fundamental forces governing the universe. Beta decay is mediated by particles called W bosons, which were predicted theoretically decades before being observed experimentally in particle accelerators. Gamma decay is the simplest conceptually but involves the highest energy. After an atom undergoes alpha or beta decay, the nucleus is often left in an excited state, higher energy than its ground state. To shed this excess energy, it emits a gamma-ray photon. The atom does not change identity. It simply drops to a lower energy level, releasing pure electromagnetic radiation in the process. Gamma rays are the same type of radiation as visible light or radio waves, just vastly higher in frequency and energy. A single gamma ray photon can carry millions of times more energy than a photon of visible light. This makes gamma radiation the most penetrating and the most dangerous. It takes thick lead, steel, or concrete to stop gamma rays. This is why nuclear reactor vessels are surrounded by massive shielding, to block the gamma radiation produced during fission reactions. Marie Curie's radium samples emitted all three types of radiation as they decayed through a series of transformations. Radium-226 decays by alpha emission into radon-222 gas. The radon further decays, producing more alpha particles and gamma rays. The decay chain continues through multiple elements: polonium, lead, bismuth, each step releasing radiation, each transformation bringing the nucleus closer to stability. The final stable product of the uranium-238 decay chain is lead-206. After billions of years and multiple transformations, uranium becomes lead. Geologists use this fact to date rocks. By measuring the ratio of uranium to lead in mineral samples, they can calculate how long the radioactive decay has been occurring, which tells them the age of the rock. This is how we know the Earth is approximately 4.5 billion years old, from uranium lead dating of the oldest minerals. A radioactive decay is a clock built into matter itself, ticking at rates determined by nuclear physics, unchanging across billions of years. And Marie Curie was the first to systematically study this clock, to measure decay rates precisely, to understand that atoms were not eternal but transforming, slowly or quickly, from unstable configurations towards stability. As we move forward, we will explore the quantum mechanics underlying this decay, the probabilistic nature that makes it impossible to predict when any individual atom will transform, and why this randomness reveals something fundamental about reality itself. Chapter 5. The Mercy of the Ray, War and Healing. Here is one of the most unsettling facts in physics. If you have two identical radioactive atoms sitting side by side, absolutely identical in every measurable way, one might decay in the next nanosecond while the other lasts another 1,000 years. There is no way to predict which will decay first. No hidden variable, no internal clock, no measurement you can perform that will tell you when a specific atom will transform. The process is fundamentally, irreducibly random. This randomness disturbed physicists when they first understood it. Classical physics operates on determinism. If you know the initial conditions of a system precisely enough, you can predict its future behavior. A ball thrown at a certain angle and velocity will land at a calculable position. A planet orbiting a star follows predictable paths governed by gravity. Cause leads to effect in ways that can be mapped mathematically, but radioactive decay does not work this way. An atom of radium-226 has a half-life of 1,600 years. This means that if you have a sample containing, say, 1 million radium atoms, after 1,600 years approximately half of them will have decayed. After another 1,600 years, half of the remaining atoms will decay, leaving you with about 250,000 radium atoms. The statistical behavior of large groups is perfectly predictable, but zoom in to an individual atom and the predictability vanishes. You cannot say when that specific atom will decay. It might happen in the next second. It might not happen for 10,000 years. The atom itself does not know when it will decay. There is no countdown timer hidden in the nucleus. The decay event is spontaneous, probabilistic. Governed by quantum mechanics rather than classical cause and effect, Marie Curie did not work out the quantum mechanical explanation. That came later with physicists like Niels Bohr, Werner Heisenberg and Erwin Schrödinger in the 1920s, but she established the experimental foundation by measuring half-lives precisely and showing that decay rates were constant, unaffected by temperature, pressure, chemical environment, or any external condition she could control. The decay came from the nucleus itself, and it followed statistical laws rather than deterministic ones. The quantum mechanical explanation involves something called tunneling. Imagine the alpha particle inside a heavy nucleus as a ball trapped in a valley surrounded by hills. Classically, if the ball does not have enough energy to roll over the hills, it stays trapped forever. But quantum mechanics allows for a phenomenon where the particle can tunnel through the energy barrier, even though it does not have enough energy to go over it. This is not metaphorical. Quantum objects exist as probability waves, not as definite particles with fixed positions. The wave function describing an alpha particle inside a nucleus has a small but non-zero amplitude outside the nucleus. There is a probability, tiny but real, that the alpha particle will suddenly appear on the other side of the nuclear energy barrier, free from the nucleus. When this happens, we observe it as radioactive decay, RALAV. The probability of tunneling depends on the height and thickness of the energy barrier. Nuclei with lower, narrower barriers have higher decay probabilities and shorter half-lives. Nuclei with higher, thicker barriers have lower decay probabilities and longer half-lives. But for any individual nucleus at any given moment, whether tunneling occurs is purely random. The wave function gives probabilities, not certainties. This probabilistic nature bothered Albert Einstein deeply. He famously objected to quantum mechanics with the statement, "God does not play dice with the universe." Einstein believed there must be hidden variables, deeper layers of reality we had not yet discovered, that would restore determinism to quantum processes. He spent the last decades of his life searching for a more complete theory that would eliminate randomness from the foundations of physics. But every experiment ever conducted supports the quantum mechanical view. Radioactive decay is random. Particle behavior at the quantum scale is probabilistic. The universe, at its most fundamental level, does involve chance, does involve processes that cannot be predicted with certainty no matter how much information you have. Marie Curie measured this randomness empirically without needing to understand the quantum mechanics behind it. She showed that if you have a sample of radium, you can predict statistically how much will decay in a given time, but you cannot predict which atoms will decay when. She demonstrated that half-life measurements were reproducible, consistent, and independent of external conditions. This was crucial evidence that radioactivity was a nuclear phenomenon governed by different laws than chemistry. The concept of half-life has become essential to many fields. Archaeologists use carbon-14 dating to determine the age of organic materials. Carbon-14 has a half-life of about 5,730 years, so by measuring how much remains in a sample, they can calculate how long ago the organism died. Geologists use uranium-lead dating for much older rocks, leveraging the billion-year half-lives of certain uranium isotopes. Medical diagnostics use radioactive tracers with carefully chosen half-lives, long enough to perform imaging, short enough to minimize radiation exposure. All of this rests on the statistical regularity of decay combined with the fundamental randomness of individual events. Large numbers of atoms behave predictably. Individual atoms do not. This duality, statistical order emerging from quantum chaos, is one of the deep patterns underlying physical reality. and it means that every radioactive atom in your body right now exists in a superposition of decayed and not yet decayed states until the moment decay occurs. The carbon-14 in your tissues, the potassium-40 in your cells, they are all quantum systems, probabilistic, waiting for the wave function to collapse, for the tunnel event to occur, for the random moment of transformation. Marie Curie studied this without knowing the quantum mechanical details, but she recognized the pattern. Decay is both lawful and random, predictable statistically, but uncertain individually. This tension between order and chaos, between determinism and probability, would become central to 20th century physics. If you are still with me in this journey through Marie Curie's eyes, witnessing the discovery that atoms themselves transform and decay, you are part of a rare community. Minds drawn to depth, to understanding, to the stories of those who change science forever. A quick subscribe helps others discover these explorations through the greatest minds in physics. Now, let us continue into how radioactivity moved from laboratory curiosity to medical treatment, and how Marie Curie brought science to the battlefield. Chapter 6. Radium in Medicine, Healing and Harm. Shortly after Marie Curie isolated radium, doctors began experimenting with it as a medical treatment. The reasoning was straightforward. Radium emitted intense radiation that could burn and kill tissue. Cancerous tumours are rapidly dividing tissue. If you could focus radiation precisely on a tumour, you might be able to destroy it while leaving surrounding healthy tissue relatively intact. Pierre Curie himself conducted one of the first medical experiments. He worked with physician Henri Becquerel to treat skin lesions using small samples of radium sealed in glass tubes. They found that radiation destroyed abnormal tissue, burned away certain types of growths, and in some cases achieved what surgery could not. The therapeutic potential was immediately obvious. By 1903, radium therapy was being tested on patients with skin cancer and other tumours. Doctors would apply radium-containing tubes directly to tumours or insert them into body cavities near cancerous tissue. The radiation damaged DNA in rapidly dividing cancer cells, causing them to die. Normal cells were also affected, but because they divided more slowly, they had more time to repair radiation damage. The differential effect meant that carefully controlled doses could shrink or eliminate tumours while allowing patients to survive and recover. Marie Curie supported this research but did not actively participate in clinical work. Her focus remained on fundamental science, understanding radioactivity itself, isolating new elements, measuring decay rates. But she recognized the importance of medical applications and helped establish standards for radium dosage and safety protocols. The Curie, a unit of radioactivity, was named in honor of her and Pierre and became the standard measure for medical radium preparations. Radium therapy evolved into what we now call radiation oncology. Modern cancer treatment uses precisely targeted beams of high-energy photons or particles to destroy tumours. The physics Marie Curie pioneered, understanding decay rates, measuring radiation intensity, recognizing that different types of radiation penetrate to different depths, forms the foundation of these treatments. Millions of cancer patients have benefited from therapies that trace their origins directly to her work. But radium's medical promise was quickly overshadowed by reckless commercial exploitation. In the early 1900s, radioactivity was poorly understood by the public. Radium glowed. It seemed magical. Entrepreneurs seized on this fascination and began marketing radioactive products as miracle cures for virtually every ailment imaginable. Radium water was sold as a health tonic. People drank it daily, believing it would cure arthritis, restore vitality, improve digestion, and extend life. One prominent victim was Eben Byers, a wealthy American industrialist and athlete who consumed multiple bottles of radium water daily for years. By 1932, his jaw had literally disintegrated from radiation damage. His bones were so radioactive that his body had to be buried in a lead-lined coffin. His death became a major scandal that finally led to stricter regulation of radioactive consumer products. Radium cosmetics were marketed to women as anti-aging treatments. Face creams containing radium promised to rejuvenate skin, remove wrinkles, and restore youthful appearance. Radium-infused bath salts were advertised as luxurious spa treatments. The radiation was damaging skin cells, causing mutations and burns, but the effects were delayed enough that consumers did not immediately connect the products to the harm they caused. Perhaps most tragically, radium was used in luminous paint for watch dials, instrument panels, and military equipment. Young women, known as the Radium Girls, were hired to paint tiny numbers on watch faces using brushes dipped in radium-laced paint. To create fine points on their brushes, they were instructed to lick the bristles between strokes. Lip dip paint was the technique taught to workers. These women ingested radium with every brush stroke. The radium accumulated in their bones, particularly in their jaws. Within a few years, many developed horrific symptoms: jawbones that crumbled, teeth that fell out, anemia, bone fractures, tumors. The companies employing them denied any connection to the radium. They fought legal battles, suppressed medical evidence, and abandoned workers who had been poisoned in their factories. The Radium Girls eventually won their lawsuits, establishing important precedents for workplace safety and corporate liability. But the victory came too late for most of them. Dozens died from radiation poisoning, their bodies so radioactive they had to be buried in lead-lined coffins, their remains still emitting radiation decades after death. Marie Curie was aware of radium's dangers. Her own health was failing from chronic radiation exposure, but she did not live to see the full extent of the commercial disasters. She continued working with radioactive materials throughout her life, handling them with minimal protection, convinced that the scientific value justified the personal risk. During World War I, she found another application for her expertise. X-ray technology existed, but was largely confined to major hospitals. Wounded soldiers in field hospitals had no access to radiographic imaging, which meant doctors often operated blind, probing for bullets and shrapnel without knowing their exact locations. Marie Curie organized mobile X-ray units, vehicles equipped with X-ray machines and electrical generators that could be driven to field hospitals near the front lines. She trained operators, secured funding, and personally drove one of these units to war zones, providing radiographic imaging that saved countless lives by allowing surgeons to locate projectiles and bone fractures accurately before operating. These mobile units were called Petites Curies, little Curies. By the end of the war, over 1 million soldiers had been X-rayed using equipment Marie Curie helped deploy and operate. She received no payment for this work. She saw it as her duty, as a scientist and a citizen, to apply her knowledge where it could do the most good. The irony is profound. Radium and X-rays, the radiation technologies Marie Curie pioneered, could both heal and harm. Used carefully in medicine, they saved lives. Used carelessly in consumer products, they killed. Marie Curie herself embodied this duality. Her work enabled radiation therapy that has saved millions. Her chronic exposure to radiation killed her. She understood the risks better than most. In her later years, she worked to establish safety protocols, proper shielding, and handling procedures for radioactive materials. But the damage to her own body was already done. The years spent stirring boiling vats of pitch blender, handling radium salts with bare hands, breathing radioactive dust, all of it accumulated, silently destroying her bone marrow and internal organs. Let us move now into the legacy Marie Curie left behind, the children she raised who followed her into science, and the final years as radiation slowly claimed her life. Chapter 7. The Curie Dynasty, a family of Nobel laureates. Marie and Pierre Curie had two daughters, Irene, born in 1897, and Eve, born in 1904. Growing up in a household where both parents were pioneering physicists meant the girls were surrounded by scientific equipment, laboratory discussions, and the constant hum of research. Marie was determined to give her daughters the education she herself had fought to obtain, and she approached their schooling with the same systematic rigor she applied to her experiments. After Pierre's death in 1906, Marie focused intensely on her daughters while maintaining her research. She organized a cooperative school with other professors at the Sorbonne, where each parent taught their area of expertise. Marie taught physics, a mathematician taught mathematics, a biologist taught natural sciences. The children received an education unlike any standard curriculum, built around direct engagement with experts in each field. Irene Curie showed early talent for mathematics and science. She was serious, focused, and remarkably similar in temperament to her mother. By the time she was a teenager, she was helping in Marie's laboratory, learning radiochemistry techniques, assisting with measurements. During World War I, when Marie established the mobile X-ray units, Irene accompanied her to the front lines, operating radiographic equipment in field hospitals at age 18. After the war, Irene returned to the Radium Institute to pursue doctoral research. There, she met Frédéric Joliot, a young chemist who had come to work in Marie's laboratory. Irene and Frédéric married in 1926, combining their names to become the Joliot Curies. They formed a scientific partnership much like Marie and Pierre had, working together on radioactivity research. In 1934, Irene and Frédéric made a discovery that would earn them the Nobel Prize in Chemistry the following year. They found that by bombarding certain stable elements with alpha particles, they could create new radioactive isotopes that did not exist in nature. Aluminum, when hit with alpha particles, transformed into a radioactive form of phosphorus. Boron became radioactive nitrogen. Magnesium became radioactive silicon. This was artificial radioactivity, the ability to create radioactive elements on demand, not just find them in nature. The implications were enormous. Scientists could now produce radioactive traces for medical research, create isotopes useful for industrial applications, and study nuclear reactions in controlled laboratory settings. The Joliot Curies had opened an entirely new field of nuclear chemistry. When they received the Nobel Prize in Chemistry in 1935, Marie Curie was in the audience watching her daughter accept the award. It was one of the last major events Marie attended. Her health was declining rapidly. She had chronic anemia, severe fatigue, and recurring fevers. She died just a year before Irene's Nobel ceremony, in July 1934, from a plastic anemia caused by prolonged radiation exposure. The Curie family thus became the only family in history to produce multiple generations of Nobel laureates in science. Marie won 2 Nobels, Irene won 1, and Irene's husband Frédéric shared her prize. 3 Nobel Prizes across 2 generations, all in the field of radioactivity and nuclear physics that Marie pioneered. Eve Curie, the younger daughter, took a different path. She became a writer, pianist, and journalist rather than a scientist. In 1937, she published a biography of her mother, Madame Curie, that became an international bestseller and introduced Marie Curie's story to millions of readers worldwide. Ev's book shaped public perception of her mother as a determined, brilliant woman who overcame poverty and discrimination to revolutionize science. Irene and Frederick continued their research through World War II and into the atomic age. Frederick became involved in France's nuclear energy program and was a vocal advocate for peaceful uses of atomic energy. Irene worked on nuclear fission research and served in government positions promoting scientific education. Both of them, like Marie, suffered from radiation exposure. Irene died in 1956 from leukemia, almost certainly caused by years of working with radioactive materials. The Curie scientific dynasty ended with Irene's generation in terms of Nobel Prizes, but the family's influence on nuclear physics, radiation research, and the role of women in science continues to resonate. Marie Curie proved that women could compete at the highest levels of scientific research. Irene reinforced that proof by winning her own Nobel Prize. Together, they demonstrated that gender was irrelevant to scientific ability, a revolutionary statement in an era when most universities still refused to admit women. Marie raised her daughters in a household that normalized scientific achievement for women. There was no question of whether girls could do physics or mathematics. The question was only which problems to tackle next, which experiments to design, which hypotheses to test. This environment produced a second-generation scientist who made discoveries as important as her mother's. The cost, of course, was steep. 2 generations of Curies worked with radioactive materials with inadequate protection. Pierre died in an accident, but Marie and Irene both died from radiation-induced diseases. The very phenomena they studied and worked to understand killed them. Their notebooks, their laboratory equipment, even their furniture remains radioactive more than a century later, stored in lead-lined containers, too dangerous to handle without protection. But the knowledge they gained, the medical treatments they enabled, the understanding of atomic structure and nuclear physics they pioneered, that legacy endures. Millions of cancer patients have benefited from radiation therapy descended from their work. Our understanding of stellar nucleosynthesis, of how elements form in stars, builds on their discoveries. Nuclear energy, nuclear medicine, radiocarbon dating, all trace back to Marie Curie stirring pitchblende in a freezing shed. Chapter 8. Recognition and Resistance. The Price of Being First. Marie Curie won 2 Nobel Prizes, became the first female professor at the Sorbonne, and discovered 2 new elements. Yet for much of her career, she faced resistance, discrimination, and outright hostility from institutions that could not accept a woman achieving what she had achieved. In 1903, when the Nobel Committee initially planned to award the Physics Prize to Henri Becquerel and Pierre Curie for their work on radioactivity, Marie was not included. Her contributions were considered secondary to her husband's. It was only after Pierre threatened to refuse the prize unless Marie was recognized as a co-recipient that the committee added her name. Even then, the official Nobel citation emphasized Pierre's work more prominently than Marie's systematic investigations that had actually discovered polonium and radium. After Pierre's death in 1906, Marie applied for membership in the French Academy of Sciences. She had 2 Nobel Prizes by then, had isolated radium through years of painstaking work, and held a professorship at the Sorbonne. She was clearly one of the most accomplished scientists in France. The Academy rejected her application. The vote was close, 30 members in favour, 28 against. But the result was unambiguous. France's most prestigious scientific institution would not admit a woman. The rejection was particularly bitter because several men with far less distinguished careers had been admitted to the Academy. The issue was not her qualifications, it was her gender. Newspapers covered the controversy, with some supporting Marie's candidacy and others arguing that admitting women would undermine the Academy's prestige. Marie never applied again. Then, in 1911, just as Marie was about to receive her second Nobel Prize, a scandal erupted that nearly destroyed her reputation. She had developed a close relationship with physicist Paul Langevin, a former student of Pierre's who was trapped in an unhappy marriage. When Langevin's wife discovered letters suggesting a romantic relationship between Paul and Marie, she leaked them to the press. The French newspapers unleashed a wave of hostile coverage. Marie was called a homewrecker, a foreign interloper. Remember, she was Polish, not French. A woman who had seduced a married man. Never mind that Langevin's marriage had been troubled for years before he met Marie. Never mind that both were adults making their own choices. The focus was entirely on condemning Marie. Protesters gathered outside her home. Newspapers published the letters. Some physicists distanced themselves from her. A few colleagues suggested she should leave France and return to Poland to avoid further scandal. The attack was vicious, personal, and gendered in ways that a male scientist in a similar situation would never have experienced. The Swedish Academy of Sciences, which awards the Nobel Prize, sent Marie a letter suggesting she should not attend the ceremony in Stockholm to receive her second Nobel Prize. They worried that the scandal would tarnish the Nobel's reputation. Marie responded with a letter that was polite but firm. Her private life was separate from her scientific work, and she had every right to receive the recognition she had earned. She attended the ceremony in December 1911 and delivered her Nobel lecture with grace and precision, focusing entirely on the science of radioactivity and radium isolation. Despite the personal attacks, Marie continued her research. She established the Radium Institute in Paris, which became a major centre for nuclear physics research. She trained dozens of students who went on to important careers in science. She served France during World War I with her mobile X-ray units, and she maintained her laboratory work even as her health deteriorated. International recognition eventually outpaced French institutional resistance. Universities across Europe and America awarded her honorary degrees. She travelled to the United States in 1921, where President Warren G. Harding presented her with 1 gram of radium, purchased through donations from American women who admired her achievements, to continue her research. American scientific institutions celebrated her with ceremonies and lectures. By the 1920s, Marie Curie was recognized worldwide as one of the greatest scientists of her generation. But in France, the Academy of Sciences still refused to admit women. That policy remained in place until 1979, 45 years after Marie's death, when physicist Yvonne Choquet-Bruhat became the first woman elected to the Academy. In her final years, Marie suffered from increasingly severe health problems. Her fingers were permanently scarred from radiation burns. She developed cataracts that clouded her vision. Chronic anemia left her weak and fatigued. She continued working as long as she could, supervising research at the Radium Institute, advising students, measuring radioactive samples with the same precision she had maintained for decades. In May 1934, she travelled to a sanatorium in the French Alps, hoping the mountain air would help her recover. It did not. On July 4th, 1934, Marie Curie died of aplastic anemia, a condition where bone marrow stops producing blood cells, almost certainly caused by years of radiation exposure. She was 66 years old. At her funeral, the French government did not provide a state ceremony, despite her contributions to science and to France during the war. She was buried in a simple grave in Sioux, next to Pierre. It was not until 1995, 61 years after her death, that France finally honoured her properly. President François Mitterrand ordered her remains transferred to the Panthéon, the mausoleum in Paris reserved for France's greatest citizens. Marie Curie became the first woman interred there on her own merit, not as someone's wife. Her legacy is written in radioactive atoms that still decay in her notebooks, in cancer patients whose lives were saved by radiation therapy, in our understanding of matter and energy at the atomic scale. She changed physics, she changed chemistry, and she proved that genius has no gender, even when the world was not ready to accept that truth. Chapter 9. Radioactivity reveals the universe, from Earth's age to stellar fusion. Before radioactivity was understood, scientists had no reliable way to determine the age of Earth. Geologists could see layers of sedimentary rock and estimate that millions of years were required for such formations to accumulate. But physicists like Lord Kelvin calculated that Earth could not be more than about 20 to 40 million years old based on cooling rates. If Earth had started as a molten ball, Kelvin argued, it would have cooled to its current temperature in roughly that time frame. This created a major conflict. Geologists and biologists studying fossils and evolution needed hundreds of millions of years for the processes they observed. Physicists calculating heat dissipation said that much time was impossible. The debate remained unresolved for decades. Radioactivity solved the problem. Once scientists understood that radioactive elements in Earth's crust and mantle generate heat continuously through decay, Kelvin's calculations fell apart. Earth was not simply cooling from an initial molten state. It had an internal heat source, radioactive decay of uranium, thorium, and potassium, that had been warming the planet from within for billions of years. More importantly, radioactive decay provided a clock. By measuring the ratio of parent isotopes to daughter isotopes in rocks, geologists could calculate how long the decay process had been occurring. Uranium-238 decays through a series of steps to lead 206 with a half-life of about 4.5 billion years. By measuring how much uranium remains and how much lead has accumulated in ancient rocks, scientists can determine their age with remarkable precision. The oldest rocks on Earth date to about 4 billion years. Meteorites, fragments of the early solar system that never formed into planets, date to about 4.56 billion years. This is how we know the age of the solar system. Not through theoretical calculations about cooling or accumulation rates, but through the radioactive clock built into matter itself. Marie Curie's work on radioactivity thus resolved one of the great scientific controversies of the 19th century. Earth was billions of years old, not millions. There was plenty of time for geological processes, for evolution, for the slow accumulation of sedimentary layers kilometers thick. And the proof came from the same radioactive elements Marie had painstakingly isolated in her laboratory. Radioactivity also explained why Earth's interior remains molten. The decay of uranium, thorium and potassium-40 in the mantle generates approximately 20 terawatts of heat, enough to keep the outer core liquid, to drive plate tectonics, to power volcanic activity. Without radioactive decay, Earth's core would have solidified billions of years ago. There would be no magnetic field, no continental drift, no volcanic recycling of materials. The planet would be geologically dead. The connection between radioactivity and stellar processes took longer to understand. For centuries, scientists wondered what powered the sun. It shines with consistent intensity, releasing enormous amounts of energy. Enough that even at 150 million kilometers away, Earth receives sufficient light and heat to sustain life. What fuel source could provide such sustained energy output? Chemical combustion was ruled out quickly. If the sun were made of coal burning in oxygen, it would exhaust itself in a few thousand years. Gravitational contraction, the idea that the sun was slowly shrinking and converting gravitational potential energy into heat, lasted longer as a hypothesis but could only power the sun for about 20 million years. Once radioactivity revealed Earth's true age, gravitational contraction became inadequate to explain solar energy. The answer came from nuclear physics, building directly on Marie Curie's discovery that atomic nuclei can transform and release energy. In stars, the process is not radioactive decay, but nuclear fusion. At temperatures of millions of degrees in stellar cores, hydrogen nuclei collide with enough energy to overcome electromagnetic repulsion and fuse together, forming helium. This fusion converts a small amount of mass into energy, according to Einstein's equation E=mc². That released energy is what makes stars shine. The sun fuses approximately 600 million tons of hydrogen into helium every second. The mass of helium produced is slightly less than the mass of hydrogen consumed. About 4 million tons of matter per second is converted entirely into energy. That energy radiates outward, eventually reaching us as sunlight. This process has been sustaining the sun for about 4.6 billion years, and will continue for another 5 billion years before the hydrogen fuel runs out. All the heavy elements in the universe, carbon, nitrogen, oxygen, iron, gold, uranium, were created by nuclear processes inside stars. Lighter elements fuse in stellar cores during normal stellar burning. Heavier elements form during supernova explosions when massive stars die catastrophically, releasing enough energy to fuse elements all the way up to uranium and beyond. Marie Curie's radium came from such an explosion. Billions of years ago, a massive star reached the end of its life, its core collapsing and then rebounding in a supernova that created uranium and other heavy radioactive elements. Those elements were scattered into space, eventually incorporated into the cloud of gas and dust that formed our solar system. Some ended up in Earth's crust. Marie Curie extracted them, measured their properties, and in doing so helped humanity understand where matter itself comes from. The connection is profound. The radioactive elements Marie studied were created in stellar explosions. Those same elements generate Earth's internal heat and provide the clocks we use to date rocks. The physics of radioactive decay and nuclear fusion are related processes. Both involve transformations of atomic nuclei, both release energy, both reveal that matter is not permanent but constantly changing. Radioactivity opened a window into the quantum world, showed us that atoms have structure and internal energy, and gave us tools to measure the age of Earth, planets, and the universe itself. Marie Curie could not have predicted all these applications when she stood in that freezing shed stirring vats of pitchblende. But the foundation she built, careful measurement, systematic isolation of elements, precise determination of decay rates, enabled everything that followed. Chapter 10. The Cost of Curiosity, What Marie Curie Teaches Us. Marie Curie knew radioactivity was dangerous. By the early 1900s, she and Pierre had both experienced radiation burns. They noticed that handling radium samples caused skin lesions that took months to heal. They observed that workers in radium factories developed health problems. Pierre deliberately exposed his arm to radium to document the damage it caused. They were not ignorant of the risks, yet they continued working with minimal protection. No lead shielding, no ventilation systems, no dosimeters to measure exposure. Marie handled radioactive materials with bare hands, breathed radioactive dust daily, kept glowing samples of radium in her desk drawer. She knew it was harmful, but she believed the scientific value justified the personal cost. This raises an uncomfortable question. Was she right? Should she have protected herself better, worked more slowly with proper safety measures, prioritized her health over rapid discovery? Or was the urgency to understand radioactivity, before competitors, before funding ran out, before the opportunity passed, worth the sacrifice she made? There is no simple answer. Marie Curie made a choice that we, from the safety of a century later with full knowledge of radiation's effects, can judge as reckless. But she was operating at the frontier of human knowledge, in an era when safety regulations did not exist, when protective equipment was not available, when the very concept of cumulative radiation damage was not yet understood. She sacrificed her health, and ultimately her life, to advance human understanding. That sacrifice enabled medical treatments that have saved millions of lives. It revealed the structure of atoms and the processes powering stars. It gave us tools to measure geological time and understand Earth's history. The knowledge she gained has compounded across generations, benefiting humanity in ways she could never have predicted. But the cost was real. Marie Curie died at 66, her bone marrow destroyed by radiation, her body so radioactive it had to be buried in a lead-lined coffin. Her daughter Irene died at 58 from radiation-induced leukemia. The Radium Girls, young women who painted watch dials, died agonizing deaths from jaw necrosis and bone cancer. The glowing beauty of radium concealed lethal danger. What Marie Curie's life teaches us is complex. It teaches persistence. 4 years of back-breaking labor to isolate 1/10 of a gram of radium. It teaches precision. Meticulous measurements repeated hundreds of times to ensure accuracy. It teaches intellectual courage, following evidence wherever it leads, even when it contradicts established theories. But it also teaches caution. The rush to exploit radioactivity commercially led to disasters that could have been prevented. Radium water, radium cosmetics, radium paint. These products killed people because entrepreneurs prioritized profit over safety, and because regulation lagged far behind scientific understanding. Marie Curie advocated for careful use of radioactive materials in medicine. She supported research into proper dosing, shielding, and safety protocols, but she could not stop the commercial exploitation, could not prevent unscrupulous companies from selling radioactive snake oil to trusting consumers. The dual nature of her discovery, healing and harming, illuminating and destroying, reflects a broader truth about scientific knowledge. Discovery is morally neutral. Radioactivity simply exists. What matters is how humans use that knowledge. Radiation therapy saves lives. Atomic weapons end them. Both applications stem from the same physics Marie Curie helped uncover. She believed deeply in the value of pure research, studying phenomena to understand them, not necessarily for immediate practical application. The Curies refused to patent the radium isolation process. They published their methods openly so other researchers could replicate and build on their work. Marie insisted that scientific knowledge should be freely available, not locked behind proprietary walls. This decision cost them financially. They could have become wealthy from radium patents. Instead, they lived modestly, struggled with funding, and watched commercial enterprises profit from techniques they had developed. Marie's choice reflects a particular philosophy of science. Knowledge belongs to humanity, not to individuals or corporations. Discovery creates obligations to share, to teach, to advance collective understanding. A commitment to education extended beyond her own research. She trained a generation of physicists and chemists at the Radium Institute. She insisted on rigorous standards, demanding precision and thoroughness from her students. Many of them went on to important careers, spreading the methods and insights they learned in her laboratory to institutions around the world. Her success did not immediately open doors for other women. Institutions remained resistant. The French Academy of Sciences rejected her. Universities were slow to hire female professors, but she'd established a precedent that could not be ignored. Her Nobel Prizes, her discoveries, her international recognition made it impossible to claim women were incapable of rigorous scientific thought. Every woman who studies physics today, who works in a laboratory, who pursues a PhD in chemistry or nuclear engineering, walks a path Marie Curie helped create. Not because she advocated for women's rights explicitly, she was focused on her research, not on activism, but because she existed, persisted, and achieved at a level that forced institutions to reckon with their prejudices. As you rest here, perhaps feeling the weight of this story, consider what Marie Curie's life illuminates about the pursuit of knowledge. Science is not a sterile, detached enterprise conducted by emotionless observers. It is human work carried out by people with ambitions, struggles, biases, and limitations. Marie Curie was brilliant but not infallible. She was determined but paid a terrible price. She advanced human understanding but could not prevent the misuse of her discoveries. Her notebooks still glow faintly in their lead-lined boxes. The radium she isolated continues to decay, atoms transforming one by one, energy radiating outward, the same process she studied more than a century ago. The half-life of radium-226 is 1,600 years. The samples she handled will remain radioactive for millennia after her laboratory has crumbled to dust, but the knowledge she gained is permanent. The understanding that atoms are not eternal, that matter can transform, that energy and mass are interconvertible. These insights are woven into the fabric of modern physics. They cannot be unlearned. They have changed how we see the universe and our place in it. As we reach the end of this journey through Marie Curie's eyes, let that complexity rest gently. Science advances through human effort, human sacrifice, human brilliance, and human error. Marie Curie embodied all of it: the wonder, the cost, the triumph, the tragedy. And her story, glowing faintly across the years like radium in darkness, reminds us that understanding the universe sometimes demands everything we have to give. If these journeys through the eyes of science's greatest minds bring you peace, a subscription helps others discover this contemplative exploration. This is Sleep Entangled, where the greatest minds in science and the mysteries they uncovered merge into voyages through science and wonder. Stay well, knowing that you are made of stardust, some of it still glowing, still transforming, still decaying towards stability. Good night.